Now we're probably only going to make it halfway through the notes today. That's fine because I've got an activity we're going to do in the middle of the notes. That's going to take probably the whole, not the whole period, but it'll take a good chunk of time. Okay. But we'll definitely get independent events done. This is section 10.5. Compound events can be independent or dependent. Independent events occur when one event does not affect the likelihood that the other events are going to occur. The example Andrea brought up with the lock. Does the probability of me getting the first wheel correct affect the probability of me getting the second wheel correct? No. It was 1/10 and 1/10. And the probability of the third wheel was also 1/10, right? They're not dependent on each other. They're independent of each other. Okay. Here's another example. Spinning a spinner and flipping the coin. Does what you get on the spinner affect what you're able to flip on the coin? No. So they're independent of each other. Okay. And so when we're working with independent events, we're going to multiply the probabilities together. If there's 2 events, multiply both fractions. If there's 3 events, multiply the 3 fractions together. We've been doing this. This is nothing new. Okay, so I'm going to spin the spinner. I'm going to flip the coin. That's 2 events, and therefore I'm going to need 2 fractions. It wants to know the probability of getting a prime number and then flipping tails. Now, who remembers what a prime number is? Anna? That's right. Only 2 factors. 1 times itself. The very first prime number is 2. 2 is prime. 1 cannot be prime because 1, although you can do 1 times itself to get 1, it's the same number. So it only has 1 factor, not 2. 2, you can multiply 1 times 2. So it's prime. 3, 1 times 3. Is there any other way to get 3? No, so 3 is prime. 4, 1 times 4. Is there any other way to get 4? 2 times 2. So it's actually got 3 factors, 1, 2, and 4. So it's not prime. And then 5. Is there any other way to get 5 other than doing 1 times 5? So it has 2 factors. Okay. So therefore, the probability of me getting a prime number is what? 3/5. 3 out of 5. The probability of me flipping tails on a coin, 1/2. Yeah, heads, tails, doesn't matter. They're both 1/2. Does the 3, because I'm multiplying here, cancel with the 5 or the 2? It will not. So I'm ready to multiply. Across the top, what's 3 times 1? And 5 times 2. My answer is 3/10. We've been doing this already. We did this last section, right? 10.4 yesterday. What's the probability of spinning a composite number? Now, prime and composite, we can think of them as almost being opposites. Prime means you have 2 factors. Composite means you have 3 or more. 1 is not composite. It's neither of them. It doesn't fit either definition. It's just got 1 factor. There was only 1 number on this spinner that had 3 or more factors. What was it, Frank? It was 4. So Frank, what's the probability I get that 4 on the spinner? 1/5. Okay. And Hunter, what's the probability that I'm going to flip heads on the coin? 1/2. I'm only doing 2 things, so I only need 2 fractions. What's 1 times 1? And 5 times 2? There's my answer. On your work papers, you need to write down the fractions you're multiplying and then just put your answer. If you want to circle it, box it in, whatever, that's fine. But I still need you to show me what fractions you were using to get that answer. Okay, so this is kind of the new part because this isn't going to make sense until I explain it. Independent events are done with replacement. I briefly talked about this a while back ago. Do you remember? I think the example I was using was putting your guys' names into a hat and then drawing out a random name every day, and that person didn't have to do their homework. Remember me talking about that? Yeah, I would never do that, but just imagine I would, right? Imagine I did. All of your names go in. I draw Ella's name. Ella's not going to do her homework. Would be weird for Ella because she's normally always on time with her homework. Okay, so Ella doesn't have to do her homework that night. If I put Ella's name back in for day number 2, does Ella's probability change? Does any of your probability change? No, it's 1 out of 23. There's 23 of you in here. Okay, it's 1 out of 23. If I draw Ella's name out on the first day and Ella doesn't do her homework, and then I put her name aside and do not replace it, does that affect her probability of being drawn? Yes. Absolutely. She's not going to get drawn again. Does it affect your probability?
Yes.
It does slightly, because now there's a 1 out of 22 chance instead of 23. So it's going to go up a little bit. And if I kept doing that, it'd keep going up, up, up until eventually you'd get selected. You'd have to be, right? Even if you were last. Okay. That's the difference between independent and dependent. If Ella puts her name back in the hat, nobody's probability is affected. Independent probability. If I do not replace Ella's name, all of your probabilities are now affected. That matters. Yes.
Why wouldn't you do that? Why can't you do that?
Because that implies that I'm giving you homework that I would feel like you wouldn't have to do. If I didn't feel like you needed to do the homework, I wouldn't assign it in general. Right? Okay. All right. So let's look at this example. It says you're drawing 3 marbles from a bag. Actually, there's 3 marbles. You're drawing 2 of them out. Okay. And you're going to replace them. There are 2 green marbles and 1 purple marble, as you can see in the picture. And it wants us to make a tree diagram of all the different ways we could draw out 2 marbles by replacing the first one after we draw it. Okay, so I'm going to put a number 1 and a number 2 inside those 2 green marbles, just so I can specify first green marble, second green marble. If I draw the first green marble out and put it back, could I draw it again the second time? I could. So I could draw that first green marble. I'll put G1. Okay. If I draw the first green marble, could I draw and put it back? Could I draw the second green marble? Okay, so I'll put G2. Could I draw the first green marble and then draw the purple marble? Could do that. I'll put P for purple. Just no number. There's only one of them. So could I draw the second green marble and then the first green marble? Absolutely. I guess that would be G1. I could also draw the second green marble and then draw the second green marble again, G2. Or I could draw the second green marble and then draw that purple marble. Or I could draw the purple, draw G1. I could draw the purple marble, draw G2. Or I could draw the purple marble and then draw the purple marble again. The key here is because I'm replacing it. Otherwise, it wouldn't be there. So if you're wondering how this works with what we were doing yesterday, how many marbles are in the bag? 3. So there's 3 ways I can draw out the first marble. If I put it back, how many marbles do I have for my second choice? Also 3. What's 3 times 3? 9. There are 9 branches on this tree diagram. Okay. Here are your options. Option 1, GG, 2 green marbles. Option 2, GG, also 2 green marbles. Different order, but still both green. Option 3, 1 green, 1 purple. Option 4, both green. Option 5, both green. Option 6, green, purple. Option 7, green, purple. I guess the order doesn't matter. You could put PG, but PG, GP means the same thing here. Option 8, green, purple. And option 9, purple, purple, PP. So of the 9 different ways that you could draw out these marbles, what's the probability that you're going to get both purple? According to the tree diagram, how many branches say PP? 1 out of 9. And if you want to confirm that, you have a 1/9 chance of drawing both green purple marbles. If you want to confirm that, you could go all the way back up to here. 1 out of 3 of the marbles was purple. And if I put it back, 1 out of the 3 marbles is purple. And so there should be a 1/9 chance of drawing both purple marbles. There's a 1/9 chance of drawing both purple marbles. That's pretty small. There is a 4/9 chance of getting both green marbles. And then there's a 4/9 chance of getting a green and a purple. And then the 1/9 chance of getting both purple. It's actually kind of similar to the homework question we looked at yesterday with the 2, you were guessing on the 2 multiple choice questions. They had A, B, C. You had a 1/3 chance of getting the first question and a 1/3 chance of getting the second question. And that was a 1/9 chance of getting them both right. So you know what's more likely than that? Getting them both wrong. You'd have a 4/9 chance, according to this tree diagram, which I know is using green and purple marbles, but imagine the green marbles being wrong answers and the purple marble being the right answer. That makes sense, kind of, right? You have a 4/9 chance of getting them both wrong. You have a 4/9 chance of getting one of the two wrong, and then only a 1/9 chance of getting them both right. So it's the same kind of problem as the one we looked at yesterday, just with marbles, where the purple marble is the correct answer and the green marbles are not. Well, you'd think like color-wise, it should be, right? But for our problem, there was only one right out of 3, so it's got to be the purple in this case. All right, so our time for our first game. And this is where I'm going to pause because the notes I won't even be up here for this. Okay, so dependent events occur when one event does affect the likelihood of the other events occurring, and dependent events are done without replacement. And that was the difference between those two games. Game number 1, we replace the dice. Everybody has a 30.4% chance of winning. Game number 2, we don't replace the dice, and the probability is always changing. It's always affected. It's dependent on what happened before. Okay, so we'll do this one tomorrow, but for tonight's homework, you can at least do all the independent problems because you've already been doing them. The dependent ones, you're going to see one noticeable difference. When you write your fractions, the denominator will always go down by 1. Because if you take a name or even a colored dice out of a hat, there's one less in there, right? That's the main difference between dependent probability. The denominator always goes down by 1. Sometimes the numerator goes down by 1 as well. Okay, we'll talk more about dependent probability tomorrow, but you can at least start half of your homework. And then tomorrow we'll finish this and then do our worksheet.